Thank you for this wonderful school. Okay, so I'll start with some prerequisites of math. So I'll present you a very first an introduction of Euclidean equivariant neural network. So first, just recall what is a group. So it's a set of elements with composition function such that there's a neutral element E that leave every element the same. For each element you have an inverse, and if you do G1 times G2 times G3, no matter how you do the operation, the order, it's not important. Okay, this is a group. So now, what is a representation of a group? It tells you how the group acts on a vector space. So you have a vector space V, and D is a mapping from the group to the linear maps on the vector space. Linear maps. So if it's finite dimensional, the vector space is just matrices. dim V times dim V. And it has to the representation of the identity has to be the identity matrix. And if you take the representation of G1 times G2, it has to be the representation of G1 times the representation of G2. And also D of G minus 1 has to be D of G minus 1. And yeah, thank you. All right. So you have two vector space. In each of these vector space, you have a representation. Let's say D for the vector space V and Q for the vector space W. And when you do the direct sum, you simply do the direct sum of the vector spaces. So in terms of coefficient of the vectors, you simply put them together in the same big vector. And in terms of matrix of representation, the representation D plus Q evaluated in G is simply a big matrix in which you have D of G here, and 0 here and 0 here, and here you have Q of G. As simple as that. And the other operation that I will need is the tensor product. So if you have again two vector space, if you look in, it's easier in component. If you have Vi and Wj, you simply create the object Aij, which is just all the possible components multiplied together, 2 by 2. And this object transform also with a representation. And it's simply, you simply have, again, D and Q. You simply have D acting on the first index and Q acting on the second index. So if I write it, I contract I with D, and I contract J with the Q matrix. And then I obtain the new element K L. So yes, 2 more things. The notion of reducible. Representation. So a representation is reducible if it exists a smaller representation in it. So if you have a representation like that, if it exists a subspace of V that is non-trivial, so it's not 0 and it's not the full space, such that if you restrict your representation to W, it is a representation. And it is equivalent to say that it exists a change of variable, such that if you apply this change of variable to G of G, the matrix will be also a block diagonal. You will have the restricted representation here and some other representation here. So from this idea, you can actually take any representation of a group and you can decompose it as a direct sum of irreducible representation. So irreducible are the ones that you cannot reduce. So you take any representation and you can always write it as a direct sum of irreducible one. And I will need this in the slide I will show you. And the last definition is equivariance. I need it because it's in the title. It's a property of a function. A function is equivariant if you have a function like that goes from V to W, to vector space, on which there is possibly different representation acting on. And it is equivariant if f of dgx is always equal to q of f of x for all x and for all g in the group. Okay, I'm done with the blackboard. So, yeah. So I want to build a Euclidean equivariant neural network. Euclidean means Euclidean groups means rotation plus translation in 3D. So what do I want to do? This is just a toy problem of what I want to do. It's a neural network that takes as input, for instance, a molecule and gives me the energy. So if I rotate the molecule, it should give me always the same ground state energy. And I want a neural network that takes as input position of the atoms and feature on each of these atoms. So for instance, the atomic number. So here I define what kind of input I want for my neural network. So points in space, and on each of these points in space, they can be many features, like many vectors, scalar values, like for instance the color of these balls. This vector, it can be the velocity or the momentum of, I don't know, anything. And now I want to define an operation for my neural network that so I have my points in space and they have some features. Let me take this. And then I want to create new features from the old features. So each point will compute new feature using the feature of his neighbors. And this will be the first operation of my neural network, and then I will repeat this kind of operations. And this operation has to be equivariant. It means that this is my input. If I rotate my input, rotate all the points and the features, and if I apply the operation, I want to get the same result as if I apply the operation and then rotate those representations. So what kind of operation am I allowed to do? So let's take an example. I have just one vector. My neighbors has vectors as features, and xba is the vector between me and my neighbors, and I want to compute a new vector. What can I do? For instance, I can take the vector of my neighbor and multiply by the distance between me and my neighbor, and it gives me a new vector. And I can do that for all my neighbors and just add them together, and I have a new vector. For instance, what else? I can do the vector product. So Levent has a vector. I take the distance between me and Levent. I do the vector product, and I get a new vector. I add all of this vector, and I have a new vector. I can do something else. I don't know. The idea is to formalize a little bit what can I do. For this, I need the irreducible representations of rotations. They are well known. They are indices, the index set by L, going from 0 to infinity. And each of these representations has a dimension 2L plus 1. So what are those representations? L equals 0 are the scalars. It's dimension 1. And these are all the quantities that do not transform under rotation, like the color of something, the temperature, the time left for this presentation. L equal 1, vectors. Velocity, gravity, dipole moment, all those quantities change if you rotate the system. L equal 2 is less familiar, but we know objects like that. Moment of inertia or stress tensor are examples like that. And there is an infinity of representations. And I will need the tensor product. And if you take the tensor product, it happens that it's like that for rotation. If you take the tensor product of two vectors, you will obtain a 3x3 matrix. And you can decompose this representation is not irreducible. And you can decompose it into a scalar, a vector, and a symmetric traceless matrix. And it's usually written like that. This is the dimension of a vector, 3 times 3, and you obtain a scalar, it's dimension 1, plus a vector, dimension 3, plus a dimension 5 representation. What I also need are spherical harmonics. So these are functions on the sphere. Here is a bunch of those. And the property of the spherical harmonics I want is that if you take, they goes like that. So there's the y0, the y1, it's the three that goes together. y2, they go together. And if you take one of those, it's an equivariant function. So it means that if you evaluate it at x, if you rotate x, it's equivalent. You can also evaluate at x for all these functions and make a linear combination, and you get the same result. So this is, again, the representation of order L, and this is just the rotation of a point on the sphere. So this is the only property I really care. The spherical harmonics have other properties. And now this is the general formula of what we can do if I want to take your features and create new feature. So this is the quite general formula. It's the most general linear formula that is equivariant and that consider just one neighbor at a time and just add all the results together. So this part of the formula, this function, is just a function of the distance between me and my neighbor. And this will be the trained, because I want to do a neural network, it will be the trained part of my operation. W are the parameters. And this is just the spherical harmonics. And it's just a function of the direction, but not the distance. And here I just do a tensor product between the spherical harmonics and the feature of my neighbor. And what I obtain when I do a tensor product, it's a representation that is reducible. And as I explained, I can reduce it into irreducible representation such that I always store irreducible representations. And I can repeat this operation again and again. So here I only presented you the linear operation. Then we need a way to do nonlinearities, but there's plenty of ways to do that. So actually there's many possible architecture we can explore, and we're only starting to developing a code to do that. So far it gave quite good results for some quantities. This is for molecule data set. QM9 is some molecules, and you have to predict many physical quantities. Like here it's the ground state energy. And here is our architecture. And for some quantities, it works quite well. Being equivariant is a good thing to be. That's it. Thank you.
Other questions? While the next speaker is getting ready?
So you have rotation
Or
group,
to ask some questions.
so you have a rotation group, but you also do translation then?
Oh yeah. Mm-hmm.
And so then how is that, can you comment how is that different from what Max Welling was doing, enriching the continents with the distance?
Max Welling, in his second talk, he was talking about a neural network acting on graphs, and in which you don't have geometry, so you don't have distance between points. You don't have directions. So his neural network has to be invariant under permutation of points. Actually, ours is also invariant under permutation of points, but it's even more constrained, ours, because it's also equivariant under rotation and translation. Yeah.
Okay, I thought also towards the end you were talking about doing equivariant with sort of smooth manifolds. It's not only a graph, but we can tell it.
Okay.
Let's see if the speakers are ready. And if there is a few questions below the slide. If not, it's fine. The next one is by
Can I keep it?
Hello everyone. Um, so I'm going to talk about recurrent random features and recurrent kernel that arise in our work with Jonathan, Moushek that's not here, and Florent. The title of the paper is Reservoir Computing meets Recurrent Kernel and Structure Transform. So what we will talk about in this talk? So we will talk about large random recurrent neural network, which is in fact reservoir computing. And we'll go to the infinite width limits, and you will see that we will obtain recurrent kernels. We will also introduce structure transform to speed up computation of random matrix multiplications. We will show a bit of concentration results of these recurrent random features towards their recurrent kernels. And we'll show you some experimental results on chaotic time series prediction. So little reminder on kernel methods, but you know everything right now. So the goal of kernel method is to use a nonlinear embedding phi to perform linear classification in a nonlinear space. Okay, and the correlation function in that nonlinear space is the kernel function. It can be expressed as the dot product of this nonlinear embedding, and you have the analytical formula of the kernel most of the time, so you don't have to compute the phi directly. The pro of the kernel method are that if in an algorithm the correlation appears, you don't have to compute this phi, you just compute the kernel directly. But the con is that if the number of points is too large, you have to compute this correlation matrix for the large number of points that you have, and it can be really expensive to compute and to store. Now, a brief recap on the random feature for approximating kernels. So basically, the random feature, it's a Monte Carlo estimate of the kernel. So you want to approximate the kernel in expectation. By doing that, you have to do that, you have to sample this W, which in fact are random. And the more W you sample, so the more random feature you sample, the closer you are to your kernel. So for instance, we're going to take random features. So if the nonlinearity is cos and sine, and you sample your W from a Gaussian distribution, then in expectation, you approximate the Gaussian kernel. So now, what is reservoir computing? So it's a recurrent neural network with random weight. So how does it work? At each time t, you feed a time series into what we call the reservoir, and the reservoir state changes at each time. And this is the update of the reservoir state. So you can see that at time t plus 1, you have a nonlinearity here, and here a square root of n, with n being the size of the projection. So I is your input, sorry. And to predict an output, O, we learn a final layer. So we learn this layer by linear regression. So what's interesting in this algorithm is that you don't have to learn these weights that are random. You just have to learn the linear regression. Whereas in the standard recurrent neural network, you have to learn this weight. So basically, what do you have is that you have a time series and you want to predict the following of the time series by using reservoir computing. So as you can see, as the update equation of reservoir computing, because W is random, you have a recurrent random feature, which means that the random feature at time t plus 1 depends on the random feature at times t. And because we know that the inner product between random feature turns to a kernel function, we can see that the inner product between two reservoirs converge to a kernel. And this kernel, we will consider two types of kernel. We will consider the rotation invariant kernel that only depend on the angle between the data point, L of t. And we will consider translation invariant kernels that depend on the distance between the data point, I of t and j of t. So you have the reservoir X that is driven by a time series I of t, and the reservoir Y that is driven by the time series j of t. So when you look at this equation, you notice that you have here the dot product, but at the previous time. So in fact, we can do this again and say that this dot product will converge to the kernel function, but at the previous time. And this is how we form recurrent kernel. We have the kernel at time t plus 1, which is equal to the kernel function of the kernel at the previous time. And you can recursively construct this kernel for all the time series. Because we know that we can accelerate a random feature using structure transform, we will use this for accelerating reservoir computing. So basically, you replace the random matrix in your algorithm by this transform. So this is composed of Hadamard matrix, which is an orthogonal matrix, which is very interesting because it can be computed in place, and DI, which are diagonal random matrix with plus or minus 1. And the advantage of the Hadamard matrix is that it's very fast to compute. You go from the computational complexity from n squared to n log n, and you just have to store n instead of n squared, with n the number of random features. So now a small theorem to show the convergence of the recurrent random feature towards their recurrent kernel. So we will suppose that we have kernels that are L-Lipschitz. We will also have to make an important assumption, which is that we resample the weight at each time to have statistical independence between the random features. And we will suppose that the nonlinearity of the reservoir is bounded by a constant kappa. And just using Bernstein inequalities, we show that our recurrent random feature turns to recurrent kernel at this rate, which is 1 over the square root of the number of random features. And also there is an important parameter, lambda, which in fact is the variance of the reservoir random matrix times the Lipschitz constant. And you have three regimes. If lambda is smaller than 1, then you converge all the time. If lambda is equal to 1, it's a linear growth of the bound, and it diverges when lambda is greater than 1. And here we have convergence rate, which shows that in practice the reservoir computing converges towards the recurrent kernel. So this is the mean square error of the reservoir computing minus the kernel. And we do it for three nonlinearities: ReLU, error function, and random Fourier features, and for different variants of the reservoir. And we show that just when the assumption of our theorem is not satisfied, which is a bounded nonlinearity, so ReLU is not bounded, then we diverge, so we don't tend to the recurrent kernel. Okay, so just a brief talk about computational complexity. So as you know, in kernel methods, it's better to use a recurrent kernel when we have a small number of points. But when you have a large number of points, you can use random features, or here you can use reservoir computing with a smaller number of random features than the number of points. And so what's interesting here is that we predict chaotic time series prediction, which is a highly nonlinear differential equation. So this is what we want to predict. And here you have reservoir computing, structure reservoir computing, and recurrent kernel. And you show that you can predict up to 2 prediction time, which is quite large actually, because this is a chaotic time series, which means that if you start at 2 slightly different initial points, then the difference between the evolution of the time series is exponential. So these results are quite good. Sorry? So this is in Lyapunov time actually. Yeah. And so during this work, we noticed something quite interesting actually. So if you don't fit any input in your time series, you say no input, but you consider the initialization of your reservoir as data, then you see that it's just a recurrent random feature but with no input. And what is very interesting is that we notice that it's just a multi-layer perceptron with random weight. And by doing so, we show that, we didn't show in this paper, but we have the intuition that a random multi-layer perceptron is in fact the approximation of a recurrent kernel. So recurrent kernel is when you make each of the layers grow to infinity, you have a recurrent kernel. And our theorem still holds in this case. And maybe we can, in future work, connect this to the theory of deep random neural networks. So as a conclusion, we studied recurrent random feature and recurrent kernel in the framework of reservoir computing. We show that these recurrent random features appear naturally in reservoir computing and converge to a recurrent kernel, then can be used to make prediction. And we haven't shown that, but the recurrent kernel is actually much more stable than reservoir computing when you have chaotic time series prediction. And what we notice that the finite-sized random neural network is the approximation of a recurrent kernel. Thank you.
And let me me also take the opportunity to thank Jonathan and also Antoine for helping me with the recordings and the logistics of the talks. That was really useful. So now you get the chance to experience it.
Yeah, I'm supposed to know how it works. Un, deux, un, deux. Yes. Hello, hello. Yes. Okay, so hi again, everyone. So I'm very glad to be here, and I'm humbled to be the last speaker to speak at the participant seminar. And today I will present something a bit different than like what people have presented before. There won't be a lot of equations. So as I'm the last presenter just before dinner, let's take some time to relax and hopefully discuss stuff that you may find interesting. So today I will talk about optics with neural networks. To start with very simple things, I will introduce linear optics. So what is linear optics? Basically, this is a lens. If we shine light with this lens, for example, we shine a plane wave, it will focus on a point. This is something that I'm sure you've already know from high school, for example, or even before when you were playing with magnifying glass to maybe burn some leaves using the sun. But if we want to put very simple equations, what's happening here? If we put an input electric field, which is constant here, then it will become a delta function at the focal plane of the lens. So for now, it's quite simple. Then, if we tilt this plane wave, what's going on? It's just going to focus on some other position. And basically, this is a plane wave in Fourier space. So basically, it's like just, yeah, it's a plane wave. This is what we call in plane wave. And it will just be a delta function, but shifted a little bit. And what is linear optics? Ta-da! If you sum the two, then the output is the sum of the two previous outputs. And you can have a look at this book if you're more interested. Basically, you can model all of optics using linear operators like this one. And for example, in this case, it's very simple. This plane, when it passes through the lens, then there is like a Fourier transform operation that is performed. All right. So now it's the more challenging part of the talk. So we'll do a small experiment. And I will ask you to all close your eyes for 30 seconds. And whenever you find something that changes with your eyes closed, then you raise your hand, just to tell me that you have seen something. Ah, cool. Okay, you can open your eyes. So basically, this was what was happening. And let's try to explain this a little bit. So when nothing was happening, it was like this. You had your eyelids, which were closed, your retina, which was here, and you couldn't see a lot of things. Then I turned on the lights, and what happened was, even though you can't really see with your eyes closed, light still can get through your eyelids. And on the output, what you can see is, it may be complicated, but light still goes through. And basically, this is done with a laser. That's why you have very strange patterns here. If we have like the sunlight, it will be much more homogeneous. All right, so, but still,
We're
what?
happy that you didn't shine on us with the laser.
Ah, yes.
Just to experience that pattern.
Yeah, we don't need to do that. But it attenuates a lot, so maybe we could try. Anyway, so if we have an electric field which is here for the input, on the output, we still have linear optics, so we still have H times E in. But in this case, this operator H depends on a lot of different particles. You have a lot of different molecules that scatter light in your eyelids, and That's what happens. So H is a random matrix. I'm sure for this community you're not afraid of random matrices, so we can go on. We can measure them. So this is, for example, an experimental measurement of a random matrix. And like, for example, it's 1,000 times 1,000. It can be quite large dimension. And something that is very important to mention is how do we play with the input electric field? What we have are stuff like video projectors or liquid crystal displays, like screens. And here we will use liquid crystal spatial light modulators. So basically an array of a lot of pixels that can modulate the phase of the input light. Basically, we can shine any image we want through the complex medium. All right, so there are a lot of examples of complex media. We can mention, for example, the fog that is present quite often here in the mountains, or also like eyelids. So basically, if we want to image deep inside biological tissue, as we will go afterwards, more deeper into, this happens. A lot of other applications, even quantum information, and shameless plug, there is also, we can do optical computing, and a lot of things related to machine learning using optics. And there is a startup, Lighton, working on this. All right, so let's go back to biological imaging. We want to do fluorescence microscopy. What is it? Basically, you have fluorescent molecules. You can excite them, and they will fluoresce at a different wavelength. So you can know where the fluorescent light come from. And for example, this is very nice because you can have fluorescent molecules that trace when a neuron is activated. So just a quick video. Oh yes, great. This is for the zebrafish. We can see the neurons activating in real time. And this is very, very important for neuroscientists because then they can get what are the systems and how does it work inside the zebrafish. But this is easy because this is transparent. So let's try something more complicated. Rabbit. Usually we use a mouse, but I found pictures of rabbits. So we'll try to do the same thing. Basically, we will use a special light modulator to shine some excitation light on the rabbit, and want to look at the brain of the rabbit, and then we'll collect some fluorescence. Of course, if you look at this, you want to look at the brain, so you have the skull, a bit like us, that scatters a lot of light. So this is quite bad, and we can't see the brain. But still, this is very important to do. Why? Because we can't just kill the rabbit to look at the neurons ex vivo, because then the rabbit is dead. So if we want to do experiments, we will need to do that non-invasively. And that's how we do it. It may be complicated. We don't know what we can do, but let's just write the equations and try to get some information out of it. So I will just have the same picture, but as a proof of concept optical setup, which is this one. So we have here the SLM, like the special light modulator, shining some excitation light on the rabbit head here, which is not like a rabbit. So here is the skull, and here are some fluorescent targets that we want to image. And on the camera, we get an image. To go a little more into the equations, here we shine some input electric fields. We'll have P of them, a lot of them. We send a lot of them, so we are probing the system. Here we'll have something which is the excitation, which is like it scatters on the way in. So we have a matrix T which corresponds to this scattering. And then we take the modulus square because we always record intensities. And on the output, we have everything is positive. We have a different scattering matrix that is multiplied by the vector here, which is how much each target has been excited. So basically, we know what we send at the input. We know what we measure on the camera, but we don't know anything here of what's happening inside, if you remember the picture with the rabbit. So we have something a bit like this. Known inputs, known outputs, and a black box in the middle. So this, you may recognize some questions that a lot of us are asking during these 2 weeks, and this is a neural network. So it's the same thing. We have the special light modulator that sends some input, E in. It gets scattered by a matrix. We don't know matrix T, so we don't know this weight matrix. Here we have a modulus square, so we have a nonlinearity. And here we have another scattering matrix, which is W. And basically, we want to find T and W for further investigation of what's happening. I won't go too much into the math, how we do it, because we do it with a very naive way. We do it with a two-step approach. So first, we see that this is positive and this is positive because it's just intensities. So we use matrix factorization because we have a sparsity constraint here. And then we use phase retrieval. So once we know this matrix, we know the activations here. And this is just a phase retrieval problem for each neuron in the middle. All right, so this is the neural network that we are looking at here. Just quickly, optics. In optics, there are a lot of neural networks. And actually, there are a lot of interesting questions to answer with like neural networks and like optimization theory in these complex landscapes. So for example, this is phase retrieval, the simplest case. We've done some works with multiplexed phase retrieval. So basically, you need to think that this is very high dimensional and this is low dimensional here. And we just record the sum of them. It's a bit like the committee machine. I looked a bit at the bibliography, and actually there are some people doing gradient descent on these kind of networks, which you may know, like with deep learning. And basically they are saying that each of these layers are some planes of the objects. So they are doing tomography and reconstructing 3D objects as light propagates through the network. And here there is also another work which is about how to optimize external parameters in some kind of optical device. And what I would like to point out here is all the theoretical works that we do here, they apply directly to optics. So it means that it's not, we're not trying to understand models which are much more complex than the toy models that we play with. Here, they're exactly what we need to investigate. So it makes a lot of sense to basically take the tools developed by our community to this framework. And actually, they don't really know what we're doing, basically. Anyway. So just quickly with the optics, there are a few, we do some cuisine, so a few steps. And we can do, for example, we can put fluorescent pollen seeds and have a look at them. So of course, this is difficult. So this is control. So this is what we should expect. And this is what we could reconstruct after all the characterization and a few steps to get some imaging. So of course, we can't get like very nice pictures that are obtained by removing the scattering medium. But still, we get some information about what is inside. Okay, so let me conclude. We have seen how to solve a two-layer neural network that appeared in optics in order to have deep fluorescent microscopy. And there are a lot of open questions. So for example, we could try other optimization algorithms. This one was the first one that we used because basically we are putting together different algorithms that we know work robustly when we have a lot of noise. Then how do we use other optimization algorithms? We could try them. The two-layer model, we don't know how many patterns we need to send to solve it. So this would be something very interesting to study. And also we had a low rank assumption in the middle. So this we could relax it and find other regularization because we know that we're looking at neurons. In optics, there are a lot of things to do, exploiting correlations which comes from physics, try other imaging settings, train real animals. And actually, there is a PhD student starting now on these topics. So if you want to discuss, there would be some applications coming out very soon. And as a conclusion, there is a fruitful interplay between optimization and optics. And if you want to discuss even after the school, feel free to reach out. Thank you for your attention. What, sorry? Yes.
Did you know that after your talk outside will look like this?
I want to thank Stefan for this picture, by the way.
Are there more serious questions for Jonathan?
Yes?
So, as far as I understand, to actually image the brain deep tissue, you need something like a 2-photon or something. You really need to.
Yeah.
But what you're showing, you really needed a wavefront to do
Yes.
it all at the same time.
So I didn't go too much into the details about this technique. Basically, people what are using is 2-photon microscopy. Yes, let's go back to this picture. They're using 2 photons here to excite. And this is cool because then you can excite very precisely in a volume. But the problem with 2 photons is you need pulse lasers. It's quite costly and expensive. And so what we're trying to do is to say, we stick with linear fluorescence with very simple concepts, and we just have complex inputs, complete outputs, and we just solve the computational patterns. So there is a hope that we can look at neurons with linear fluorescence, which is much easier to use than two-photon fluorescence.
This is just a modulated laser wave pattern.
Yes, just a modulated laser. It's continuous wave laser, the most simplest thing.